Assalamu alaikum, Molweni. Good evening, Goeienaand, Mahaha, Bonsoir, and Bawanote to all our attendees from South Africa and international. So yeah, we have gone international. So my name is Tokir Ahmed, and this is the Fireside Chat in collaboration with the SAICE Academy. And thank you for those connecting with us today. We hope that today's topic will be thought-provoking, as always, for you. And again, thank you for your support in continuously joining the session month on month. It's much appreciated. Today's event is our 13th Fireside Chat. We encourage you to visit our YouTube channel, SAICE TV, for all our previous Fireside Chats. We will share the link in the chat so that you can just connect to that SAICE channel. And then, yeah, if you are watching this on YouTube, like and subscribe down below and hit the bell icon so that you can turn on the notification and obviously be notified as and when new videos get uploaded. So for those who are new to this platform, just a quick recap. So these discussions are aimed at stimulating debate and discussion, mainly around civil engineering, innovation, smart technologies, matters of mutual importance to civil engineers, and engagement and collaboration with other organizations and other fields of engineering, such as electrical and mechanical engineering. As you know, civil engineers are not in isolation. We need to engage, with other fields of engineering as well. And besides that, wider as well, such as operations and logistics. We are an integrated society, and your uh, infrastructure and assets are also integrated at the end of the day. So we host these events on the second Thursday of every month. We engage with professionals, academic, professional bodies, and the industry to have a nice balanced discussion. Again, as much as we are focused on civil engineers, the discussion is also open, to everyone. We welcome everyone from all professionals, professional environments. If you are, in the banking field, finance, human resources, we encourage everyone to join so that you can get insight in what we do as civil engineers. We also actively, and encourage your participation, the audience. Please feel free to raise your hand and ask a question, live during the Q&A session, or when we have that, the panel discussion, or drop your comment or question in the chat box, at any time. Please feel free, and we'll do our best to then address them. If not in the session, then through a follow-up, via email. We also kindly request you to then rate this session. So we'll also be dropping an assessment questionnaire and form. It does help us to then, be quite specific in terms of, what we give you as a service offering, and to just test ourselves, make sure that we are still being relevant and we haven't missed the mark. So today's main topic is going to be about colloidal silica. So what is colloidal silica? So obviously our presenter will then give us an overview, but very basically it's a dispersion of fine silica particles in liquid, and it can be used innovatively for sustainable concrete construction, besides just a few other applications. So in civil engineering, we are constantly seeking new ways to enhance the durability and performance and environmental footprint of our infrastructure. This requires commitment to continuous improvement, research, and responsible adoption of new technologies. Colloidal silica, for instance, represents one such area for innovation, and is being explored, in concrete technology. While the underlying scientific principles and its use in specialized applications have a history of spanning over plus minus 30 years, its broad application in general concrete construction highlights the ongoing evolution within our field. So it's new technology, and we'll also then explore that today. And our primary goal today is to facilitate a balanced scientific and practical discussion around such advancements when it comes to innovation within established principles within civil engineering. We aim to explore the complexities, challenges, and opportunities that emerge when we consider innovative materials and approaches for sustainable construction. Embracing innovation often involves, navigating questions around long-term performance, integration with existing standards, and perceived value to new approaches. So it's always a field that we can get a bit cautious around it, but again, we need to be open-minded when it comes to new technologies. So I would like to then delve into these aspects, in today's discussion. and foster a nuanced understanding of how we can collaboratively drive progress. Because at the end of the day, we need to progress, in the different fields that we work in, and it needs us, to be open-minded and work balanced, as we go forward. So again, we want to encourage an open dialogue. So your question and your perspective are quite vital. So again, we encourage you to please, drop your comments and questions in the chat, or raise your hand when the opportunity comes, so that we can have a truly enriching, session. So yeah, let's explore how continuous innovation can contribute to building a more durable, sustainable future for our built environment. So to take us through the discussion, we have then invited two distinguished panelists. We've got Brent Rowland from Spraylock. He will be our main presenter for today, and he brings with him an invaluable, industry experience and a deep insight into the practical application of, innovative concrete materials. Then we also have Dr. Lewis Parsons. So he's not new to us. He's been with us, in a few of the panel discussions. So yeah, so from his side, he's quite deeply involved in cutting edge, concrete research. Notably, his work just around, recycling, waste into concrete, specifically e-waste. So we did have him a few episodes back, and you can have a look at that on the YouTube channel. An interesting discussion we had there around e-waste and how you can recycle e-waste back into concrete. So yeah, so I don't want to, obviously, introduce them, too much into detail. Let me allow them to come, forward and, give us, some insights into who they are. So let me start, Brent. If you can just put on your camera and just briefly introduce us and just tell us, who you are and what you do.
Thank you so much, Takir. It's really a pleasure and an honor to be here this afternoon with everyone. I'm a fan of your organization and what you're trying to do to advance knowledge. So I'm humbled by the opportunity.
Thank you, Brent.
I'm a career concrete guy. It's all I've ever done. My father was in the ready mix concrete business, and when I was 16 years old, I needed a summer job, and I was looking for an air conditioned space like a bookstore or a movie theater, and like all my friends, and none of those places were hiring. So my dad put me to work at the concrete plant, and I quickly fell in love with it, and spent the next 20 years on and off in the ready mix concrete industry, eventually getting to work on some really nice large projects. But I really enjoyed troubleshooting as well, figuring out problems with concrete and how to fix them. So that led me eventually to the University of Tennessee, Chattanooga in 2010, where I spent 7 years as the civil engineering materials research lab director. So I had a fold out business card, it was a long title.
Yeah.
And then in 2017 came to Spraylock Concrete Protection, one of the world's leading providers of colloidal silica for concrete. So that's me in a nutshell. The main thing to remember about me is I love concrete, but I also understand that it is a material that we are continually learning about, and it continues to evolve. So no one knows everything there is to know about it. I hope that my experience comes across today, and the presentation's valuable.
No, thanks, Brent. And no, thank you for your passion as well. I mean, that's what we want. We want passionate, individuals, so you can feel that passion, and it helps with the learning experience. And yeah, I must say, concrete is quite an interesting material. I mean, the older structures come from the Roman times, and it's interesting to see how they made concrete. And I recently came across, something or an article that spoke about, the Roman concrete, where they actually cooked the concrete, and then the materials, of such a nature that it was almost like self-healing concrete. So
Yes.
yeah, which is quite interesting, and perhaps we need to go back to some of those old methods. But yeah, no, it's very versatile material. Thanks, Brent.
Thank you.
And then Lewis, if we can just get you to also come and just introduce yourself.
Hi, it's okay. Can you hear me?
Yes, we can.
All right. So yeah, good evening, everybody. My name is Lewis Parsons. I'm a lecturer from the School of Civil and Environmental Engineering at the University of the Witwatersrand. My field of interest is in concrete sustainability, with a focus on the alternative construction materials. I'm also a concrete guy, similar to what Brent was calling early on, and so my passion is also lies within concrete, focusing on both the aggregate as well as alternative binders.
Perfect. No, thanks, Lewis, and yeah, looking forward to an interesting discussion later on, and then to get your views and perspectives as well. Okay, so that's our presenter. So then, Brent, I think let me then not hold you up too long. Over to you. If you can just put up your presentation, and then we'll let you carry on.
Excellent. Thank you so much, Takeda, and thanks to everyone for attending. So as Takeda mentioned, passion's important for a presentation to keep everyone's interest, and I hope to be entertaining today as well as informative. I'll try not to make too many cheesy jokes and those kind of things, but the good thing is, if you want to throw things at me, then you're going to have to throw it an awful long way because we're across the ocean. So let's get started. So some of you may be familiar with, and many of you may be familiar with the idea of a sustainability life cycle. It is what is considered when we're talking about greenhouse gas emissions regarding any material production, specifically for construction projects. We'll be talking specifically to concrete construction projects involving this cycle today. But I wanted to point out that most organizations that I'm aware of and in the US and elsewhere are concentrating mostly on what's called a cradle to gate greenhouse gas or embodied carbon perspective. So in other words, from raw material extraction through to product manufacture and leaving the site, or in some cases arriving at the project site. And that's a good approach. It's a good first approach, but it mostly concentrates on the embodied carbon of the manufacturing process, which is fine, and that's something we should do. For instance, in the U.S., we have recently begun in the last few years, cement companies have been including up to 15% limestone in their clinker. And that's what is known as the 1L cements. It's a ASTM C595 1L cements. That's all well and good, but what we're finding, great to reduce the carbon footprint of cement. They're taking out 15% of the clinker. However, it has resulted in a few problems across the country, mainly with the increased grind that has to be put on the cement to accommodate for that 15% less clinker. We've seen water demands increase in some areas, not all, but some areas have seen water demand increases. And as you know, as Duff Abrams first published in 1918, if you put more water in concrete, it's going to be weaker in general. So we've had some issues there, and we're hopefully going to be recovering from that, and it looks to be progressing. But I mentioned that just simply because cement companies are global organizations in many ways, and many of them are multinational, huge corporations. And they have a stated goal of reducing the embodied carbon of cement. So we're going to talk in the panel discussion possibly about what the future might hold. So I'll leave that for then. But for now, where we are is mostly cradle to gate analysis in the embodied carbon of what it takes to make a cubic meter of concrete. And what we're going to be discussing now is an alternate approach, or an additional approach that I believe we should be considering, which is cradle to grave, meaning that you take into account the life expectancy of your concrete structure so that you can have an annual average embodied carbon for the life of the structure. I think that the length of service life is something that is currently being overlooked a little bit, but we will talk about where things are going with the American Concrete Institute, for instance, as well as reference some FIB information during this conversation today. So to start with, just to refresh everybody on Portland cement concrete and sort of the basics, and this is important to understand where colloidal silica fits in. So I know most of you probably know this, and you're going to be looking at the next 2 or 3 slides and say, Brent, I didn't sign up to learn the basics of concrete. but I'll touch on it, and then I'll show you where colloidal silica fits in. But first, I'm going to share some statistics. Did you know that concrete is the second most used substance on the planet, behind only water? In fact, 2 times as much concrete is used as all other building materials combined. That's a tremendous amount of concrete. To put that into perspective, we make enough concrete on this planet to go to the moon and back 48 times with a 4-foot wide or about a 1-meter sidewalk, somewhere around 100 mils thick. You could go to the moon and back 84 or 48 times with the concrete we make on Earth. That's a lot of concrete. But the problem is that too much of that concrete is replacement concrete for concrete that has failed or aged and needed to be replaced. We think of concrete as being a permanent thing. We think of it, I mean, if you refer to an idea as a concrete idea, that means it's solid. It's something that's going to last a long time. It's got huge implications. Well, when we think of concrete as a permanent material, we're giving it some credit that it doesn't deserve. It's a good material. It's a great material, but it doesn't last forever. We're going to dig in a bit to just what the causes of that could be and why our concrete isn't lasting as long as maybe we'd like to see it last. So we use so much concrete because it can be cast into virtually any shape, especially with the new chemical admixture technologies that allow things like self-consolidating or self-compacting concrete. It can take on the shape of a form. In years past, in the 1960s, you could get concrete in any shape you wanted, as long as it was square, rectangle, or in the shape of a pipe. So now you really can get concrete in just about any shape that you want. Concrete does carry loads. It does what you engineers want it to do, which is to hold up buildings and resist things like wind loads and live loads. It is durable compared to other building materials, and it can be green. Excuse me. And what I mean by that, I've got some water here, not anything else. It can use recycled materials. It can even reduce the heat island effect, which is just by quick note, the dark colors in an urban area. Dark colors in an urban area absorb sunlight. Dark roofing materials and dark paving materials generally cause an urban area to be a few degrees warmer than the surrounding countryside. So by using concrete, we can, Portland cement concrete, we can produce a lighter, more reflective surface that reflects more sunlight than absorbing it, and thus lower the temperature of urban areas. So that's one way concrete can be green. So concrete, again, we're not going to spend a lot of time on this, but fundamentally, concrete is made from Portland cement, coarse aggregate and fine aggregate, and water. That's all you need to make concrete. That's the way we've been making concrete for a long time. However, most concrete, modern concrete, uses something known as supplementary cementitious materials, or pozzolans. In some cases, like in Europe and I believe in South Africa, that pozzolan is often interground into the cement, like what we're doing with the limestone here, or it could be potentially in some markets purchased separately and stored in a separate silo to be then weighed up separately from the cement. And you're going to see why. I'm going to talk about why I chose a picture of a volcano for the pozzolan to represent pozzolans or supplementary cementitious materials shortly. But most of our focus in this concrete discussion is going to be on pozzolans in the next few slides. Most modern concrete also contains chemical admixtures, and chemical admixtures exist to do just about anything you'd like to have your concrete do. And what I mean by that, if it's cool and you want it to set quicker, then you can accelerate the setting time with something called an accelerator. And if it's setting too fast in the summertime, you can slow that down with a hydration stabilizer. You can use water reducers to make the concrete move without adding water, for instance, and on and on. So again, our focus is going to be pozzolans. for now, because I want to show you where colloidal silica fits in. All of these materials that you see on the screen have been used in the past for cement replacement and or addition. And these materials have some pozzolanic capabilities. And all that means is, well, let me pause there because I'm going to need to explain the volcano at this point, as I promised to do. The volcano just simply represents the earliest discovery of pozzolanic materials. And Tequila mentioned the Roman concrete earlier. Well, Rome's surrounded by about 70 volcanoes. And one of those volcanoes, the most famous, Mount Vesuvius, erupted in the year 70 and scattered ash throughout the countryside. And the Romans found that when they would incorporate this ash into their concrete, that the concrete was more workable, got better strength, and seemed to be more durable. So they began using this ash. Well, that technology was lost for several centuries. And then in the early 1920s, a Cal Berkeley researcher posited that ash from coal could have some effects on concrete. And thus, fly ash was born. And fly ash is the most widely used pozzolanic material from coal burning power plants across the globe. However, as we adjust our power grid and we start looking at materials that are materials and processes that are not coal burning, fly ash has started to become in short supply in some markets. I think we still have quite a bit to go through, but it's caused us to start looking at other pozzolans. And all of these other pozzolans that you see are supplementary cementitious materials. I use those terms interchangeably. They're not exactly the same, but a pozzolan basically, the word comes from that volcanic ash that the Romans called pozzolana. So when we rediscovered that pozzolanic activity, we sort of Americanized the word and called it pozzolan instead of pozzolana because pozzolan's a little easier to say. But the thing that we have in common between or among all of these materials you see on the screen, the one thing that's in common is something called amorphous silicon dioxide. That amorphous silicon dioxide is very important to concrete strength and durability. And we're going to look at that a little closer on the next slide. But that's the commonality between all of these products. The active ingredient is amorphous silicon dioxide. Now, there are other active ingredients in some of them, but the major one is that silicon dioxide. Colloidal silica is just a pozzolan in many ways, chemically identical to some of the pozzolans that we see on the screen, but much, much smaller. Because of its extremely small size, it has the highest chemical reactivity of all the known pozzolans to date. So it's the most chemically active we've discovered so far. But that size, that particle size, is super important. So let's get into why that pozzolanic reaction works, what happens. So this is a bit of a science class, but it is simplified. And I took this from some slides from Georgia Tech, famous Georgia Tech professor Kimberly Curtis. She's the originator of this slides idea. I use my own images though. So if we take cement and we add water, magic happens, right? The cement begins to harden, it begins to gain strength, and that is a chemical reaction that's occurring that produces, among other things, calcium silicate hydrate. So that calcium silicate hydrate is the major reaction product that gives concrete most of its strength and durability. Among other reaction products, there's one called calcium hydroxide that is also produced. That calcium hydroxide really doesn't add much to strength or durability. It just sort of sits around in the concrete waiting on something to react. Well, along comes pozzolan. If we put pozzolan in the concrete, whether it's mixed in or somehow applied later, as we'll see, you get a chemical reaction that happens that consumes some of that calcium hydroxide or portlandite. to produce, guess what? More CSH. That same reaction product that produces that strength and durability that we want with concrete. The pozzolan produces that secondary CSH. So that's the key reaction. And when you bring colloidal silica into that, being a pozzolan, that is the reaction for colloidal silica. However, colloidal silica is able to produce this reaction much more efficiently because of its small size than the other pozzolans. The reason this is important is concrete's permeable. We don't think of it as being permeable. We think of it as being a hard, solid substance that lasts forever, right? But the reality is that all concrete, almost all concrete, I don't want to say all, but almost all concrete is made with more water than is needed for that initial chemical reaction to take place. There's a few reasons for this. Number one reason is that the chemical reaction between cement and water is not just a one and done reaction. It doesn't just happen on day one and then stop. The reaction begins as soon as water and cement meet each other in the mixer. The reaction starts to progress and build heat at various speeds, depending on temperature and grind of the cement and some other things. Then it's placed. And when it's placed, some of that water that is in there to allow us to place that concrete leaves through bleed water channels and capillary void structure. So you have some evaporation of that extra water, that water of convenience that we use to help place concrete. Some of it leaves during the setting process. What happens with that is that the little rivers that form, or the little capillary void structures that form, then become set in space as that concrete hardens. Now, I don't want to make it sound like they stay the same size throughout the concrete's life. They do fill up gradually over time with reaction product, but you have a route of ingress, a way that water and the contaminants that water carries to get into the concrete now, because of those little tunnels that were formed as the concrete was setting. This is what it can look like under a scanning electron microscope. Now, this is an extreme example that I chose specifically for illustrating this, but you can see that the texture looks very much like a sponge. Now, it's not soft. If you ever rode a bicycle as a kid and fell and skinned your knee on a sidewalk or a driveway, you know it's not soft. But this is the culprit. This permeability is the culprit for why our concrete isn't lasting as long as we want it to. And to illustrate that, the background of the slide here, you see in the bottom right-hand corner a reddish-brown stain on the surface of the concrete. This is from a project that I was asked to take a look at in New York City a few years back. This was a raft slab in the basement of an underground parking garage under a high-rise building. And you can see that there's various moisture across the slab. And what I mean by that is you can see the darker areas that look wetter, the lighter areas that look drier, and then this reddish-brown stain. Some of you may have already put on your Sherlock Holmes hat and said, yes, I know what that is. It's rust from reinforcing steel. The movement of water from the ground up through that slab has caused rebar corrosion to start, and the reaction products of that rebar corrosion are often reddish brown in color, and you can see that here. So I wanted to share that as an example of what that permeability can lead to, and it can lead to the loss of reinforcing steel section. So if you remember your calculations from school or what you work with every day, you know that as you lose reinforcing steel section, you're losing the ability to carry tensile flexural loads. So that is a major concern when it comes to concrete durability. All right, so I spent a lot of background on this, but I'm not asking, or spend a lot of time on the background. I'm not asking you to believe me on any of this. The Portland Cement Association, based in Skokie, Illinois, has a great definition. Many others have good definitions on permeability and durability. But the reason this permeability is important is because it directly affects the durability of the concrete. As permeability goes up, durability goes down, and vice versa. If permeability goes down, then durability goes up. And you guys have some wonderful concrete engineers in your country. There are several that whose publications have influenced my career, including Professor Mark Alexander, as well as Professor Hans Baushausen and others. Everyone knows, the guys that study concrete durability know that permeability is the key, and measuring that permeability and measuring improvements to that permeability is the key to predicting service life of concrete. That's important because our concrete isn't lasting as long as we want it to, as we mentioned earlier. Back in 2012, the American Society of Civil Engineers, ASCE, it's a wonderful organization. They put out a publication in 2012 that gave our infrastructure in the United States a D minus. Almost a failing grade is what that means. If you think we do letter grades in the U.S., A, B, C, D, and A is the best, D is the lowest that could pass a class, D minus is lower even still. What they found was that 1 in 6 bridges in the United States needed to be repaired or replaced back in 2012. That's not good because we have over 600,000 bridges in this country. And that means that over 100,000 bridges at that time were in bad shape. And I hope that we've made some changes and improvements. And I hope to be able to report back to this group that we've fixed everything, but we're not quite there yet. So the reason that I mentioned bridges, by the way, is bridges are publicly funded in general, and because of that, their inspection records, as well as publications surrounding bridge technology, are public record and are accessible. And they're the most studied concrete elements, really, in my country and maybe even on the planet. But it's not just bridges that are having a problem. You know, I have a favorite saying that concrete doesn't know what it's going to be. Concrete might be a beam, like you see in the picture, or it could be a bridge deck, or it could be a foundation. That concrete doesn't know what it's going to be, but it knows, or we know, it's going to be permeable. And it's going to allow water and the contaminants that water carries to get into that concrete. Now, this photo is an extreme example of that reinforcing steel corrosion that I was talking about. You may have seen some of this in some of old projects that you've looked at. What you had happen here is the bottom of this beam, the reinforcing steel began corroding, and the reaction products of reinforcing steel corrosion take up at least 4 or 5 times the volume of the original steel. So as that steel begins to corrode, it grows. And when it grows, it exerts tensile stresses on the concrete that eventually blows the face off the concrete, something that we refer to as a SPAL, or a reinforcing steel delamination, or cover concrete delamination, etc. So that's the key function of what permeability can do to reinforce concrete. So ICRI, the International Concrete Repair Institute, estimates that concrete buildings in the U.S. alone take between $18 to $20 billion in repairs every year, and that those buildings are generally only expected to last 50 to 60 years. I did a study on municipalities a while back, and some of those municipalities, some of those cities are seeing sidewalk lifespans of less than 5 years. Now, we have something in the U.S. that you guys don't get too much exposure to in South Africa, and that's freeze thaw and de-icing chemicals, especially in the northern states. And I will say that most of the municipalities that I talk to that are having short lives on sidewalks, it is due to de-icing chemical attack, whereas you guys and the beautiful coastline you have there in South Africa, much of your salt attack is going to be coastal salts. But we're not just talking about salt attack here. We're talking about permeability and all of the things that can affect concrete. It just so happens that reinforcing steel corrosion is the number one reason. So we're going to spend quite a bit of time on reinforcing steel corrosion. So, all right. So now we get to what is colloidal silica and how does it work? And thank you very much for your excellent introduction, Takir, and the information that you gave us was spot on about colloidal silica. It's amorphous silicon dioxide on the nanoscale. That's all it is. But to understand that small size is important in understanding the function of colloidal silica for two reasons. A nanometer is 10 to the negative ninth meter. So we're talking about a billionth of a meter. That is a tremendous amount of tiny, tiny particles that you can put into concrete. And I'm going to use some examples. That photo of a pore structure that you see is about 20 microns in diameter, or about a third of the average human hair diameter. If we assume that that hole is as deep as it is wide, it will hold about 700,000 average size colloidal silica particles. That small size allows that colloidal silica to get to over 99% of the interconnected pore space in concrete. So to put that into further perspective, I know you guys like rugby there. If you imagine that average colloidal silica particle is about the size of a rugby ball, then the average pore structure in concrete would be about 3 kilometers wide. So that's how tiny we're talking. We're talking about a very, very small material, and that size is the key to its effectiveness because it gets in deep, really, really deep, and it also is able to have very high reactivity because of that small size. That small size translates to surface area. You can see across the bottom of this graph, the x-axis is a log scale, and you can see that it is in nanometers. Coarse aggregates here, about a 20 millimeter coarse aggregate's going to be in the neighborhood of 10 million nanometers. So up to 20 million, somewhere in that neighborhood. And then as it gets smaller and smaller, you can see that the surface area on the y-axis goes up. Most conventional concrete deals with these materials here. Then when you start getting into high strength or high performance concrete, then you start using finer and finer ground materials to make sure that the particle packing is going to take place properly. And that's a key to both permeability and strength development in some of these high strength mixes. You start using some exotic pozzolans or supplementary cementitious materials like calcined clays, metakaolin, etc. Silica fume is another one of those exotic pozzolans. And I say exotic just meaning that not often used. But colloidal silica right now is the smallest of the small and is producing a tremendous amount more surface area per kilogram than any of the other concrete making materials. In fact, Professor Konstantin Sobolev is who I borrowed this graph from. He wrote a book called The Next Big Thing is Small, Nanomaterials in Concrete. And that's where this graph comes from. But the tiny, tiny size, again, is key for penetration depth as well as surface area and reactivity. Colloidal silica can be put in the mix, but most often what we see effectiveness-wise is to apply the colloidal silica by spraying to the concrete surface where it enters the concrete. Again, its small size allows it to get deep, and what we've seen in the laboratory on a very dense mix with about a 0.30 water to binder ratio is 38 millimeters on a 100 millimeter slab is the least that we've ever measured. We usually see somewhere between a half to a third the depth of the concrete member, and it can be applied horizontally, vertically, or even overhead. Now, that application process, just to give you an idea of what it looks like, the spray is happening. You're applying very much like a traditional spray applied curing compound or sealer, but it does only take one pass. With a 50% overlap, you apply to a quantity to an area. So you'd have X number of liters per square meter, for instance, and it enters the concrete where it reacts, closes that void structure with a reaction product that is common to concrete, CSH, calcium silicate hydrate, the same reaction product that gives concrete strength and durability. So you're essentially, this is the beauty of colloidal silica, you're essentially filling void structures with more concrete. It's a permanent change to the microstructure. It can't be removed, and it's deep. So the only way to get rid of it is to remove the concrete itself. So I want to share some real science with you, though, because I don't want this to sound like a sales presentation. There was a PhD study that was sponsored by Total Energies in France a few years back. Student's name was Badreddin El-Haddad, and I'm grateful to be able to say now Dr. Badreddin El-Haddad. And it was overseen by some of the biggest names in the concrete industry, including Nicholas Roussel, who's current chair, if I'm not mistaken, of FIB, as well as former MIT Concrete Sustainability Hub chair. And I'm blanking on his name right now for a second, but some nice big names. But to bring it to the information I want to share to light, well, let's take a look at this graph. So you can see the log diameter in nanometers of the pore structure. This is a neat cement paste that was studied. And you see different water to binder ratios. Now, the graph was in French, so that's what the E/C is. Think of it as W/B. And you see about 0.4, 0.5, and 0.6. And you can see those dotted lines. You have an average pore diameter in the case of the 0.4 and 0.5, greater than 100 nanometers. In the case of the 0.6, right at 100 nanometers, or sorry, the 0.4, right at 100 nanometers. The colloidal silica, what they're calling nanosilice in French, was applied to the surface of the neat cement paste, and then the pore structures examined again a few hours later, and you can see that the average pore diameter went from being above 100, and it was the 0.6 that was treated, by the way, with the colloidal silica. The 0.6 was adjusted from well above 100 nanometer pore diameter down to about 30 nanometer pore diameter. So that reduction in pores in a neat cement paste is a demonstration of what the product can do for concrete. So this was ESITC in France, and they're one of the top technological universities in that country. So what does that mean for durability? Now, I made a promise to you guys that I would be, I've got about 10 minutes left, that I would be talking about sustainability. And all of this presentation has led us to this point. This won't take long. You see here, this is life cycle modeling, software modeling with Life 365, which is an industry developed life cycle modeling for concrete. It's a corrosion model only. It's got some FIB code as well as some historical information that feeds it. But you can see that the colloidal silica treated concrete compared to the Portland cement, plain Portland cement concrete was a 20-year life cycle at this particular coastal location. And this is the shoreline exposure. And you can see that with colloidal silica, it's expected to last 50 years. So from 20 years to 50 years. So what that means is that impact on total life cycle of the structure, greenhouse gas emissions impact. You get an untreated controlled concrete, 20 years of service life. Treated concrete's got 50-year projected service life. What that turns into is, if we assume 10,000 tons just for a round number of CO2 equivalent embodiment for the project, At the end of 50 years, the embodied carbon of the control concrete, assuming full replacement, would be 25,000 tons if we didn't treat it with colloidal silica. If we did treat it and you did get the 50 years design life out of it, then that embodied carbon would still be about 10,000 tons. So you can see a multiplier of 2.5 in this particular case. So what I'm proposing is that we learn more and we work harder to be able to use predictive modeling to predict the life cycle of our concrete structures more and more accurately. And there's some good models out there, but we need to close the loop. We need to work hard to make sure that these models are producing reliable results. So that's the key to the discussion. Let's make our concrete last longer. And by doing that, we can make a long-term sustainability impact. Now, colloidal silica has been used on all of these things to slow penetration of chlorides and other contaminants, bridges, parking decks, driveways, parking lots, sidewalks. Again, concrete doesn't know what it's going to be, but it's all going to be permeable to some degree. Let's close that permeability and shut down the transport of those harmful materials that get into concrete. I've got a couple minutes. I want to share a couple of quick example projects. This was, and colloidal silica can be used on new concrete, or it can be used to treat existing concrete. If you treat existing concrete with it, the main thing you got to remember is that the material must be able to get into the concrete to be effective. And sometimes that requires mechanical opening of the concrete surface with things like grinding or shot blasting. This particular project, you see the pictures here, is a tunnel in Chattanooga, Tennessee, that was built in 1938. The tunnel had received very little maintenance throughout its life, and in 2015, the city decided to refurbish the tunnel. The tunnel is it's almost 2 kilometers long, so it's a decent sized tunnel, and it was leaking really, really badly. So the city began doing the work, and they were using crack injection, and they had used up 75% of their crack injection before they had made it a quarter of the way through the tunnel. And I got called in as a consultant. I was still at the university in 2015, and they asked me what I thought they could do to help the concrete. And I helped convince them that they should use colloidal silica to try to manage that permeability through the concrete. Now, you had water coming through cracks, but you also had water coming through the matrix of the concrete. So once we treated it, we cleaned it good, treated it with colloidal silica, they were able to finish the rest of the tunnel with the remaining 25% of the injection material. So they were able to do 3/4 of the tunnel with the remaining 25%. And the reason was the colloidal silica would go into the cracks, seal the sidewalls of the cracks, and that would cut down on crack chasing as they're injecting the cracks. So I wanted to share that. Looks like we're out of time. We did have a couple of other projects. Just throw up a really quick photograph. The other thing that can happen with colloidal silica and sustainability is just the resistance to the natural environment. The concrete you see here is at a university in the U.S. This was placed 3 years before the concrete at the bottom. The top concrete was placed 3 years before the concrete at the bottom. The difference is the top concrete was treated with colloidal silica to close that void structure. And you can see that it didn't have all the little capillary void structures for all the nasty biogenic material to grow. So that's it, guys. Again, if you can keep chlorides out of your concrete, that's the #1 way that you can help your concrete last longer. So thank you so much.
No, thank you. Very much appreciated. Very interesting discussion or presentation. A lot of things to think of. I recall doing concrete technology when I was still in my studies. A lot of reminders and a lot of things that we can relate to. From my side, we are more into the maintenance of concrete and concrete structures. So it's quite important that you need to look after your investment at the end of the day as well.
Absolutely.
So colleagues, we'll just have a short, just like in a panel discussion. So there's a few, questions I had, prepared for the panel members. Just have a short debate, and then we'll come over to you for your hands and your questions. Um, just one quick question, if I may, Brent.
Yes.
Besides what I had then shared with you before, now colloidal silica. Now, obviously, you're showing it as post application. And just correct me as well. My understanding is that it also helps to reduce the water required. Uh,
Um,
what I'm asking is that should you not be mixing it in with the concrete to reduce the water need versus post application?
Great point. So integral colloidal silica or mixed in the concrete is a excellent way of introducing it to the concrete. What it can do is produce, because of its shape, colloidal silica is spherical and it's a bunch
Yeah.
of little nanomaterials in a spherical shape that fill in voids, as you can imagine, in a concrete mix. So it increases workability and reduces the amount of effort that it takes to move the concrete. It doesn't really act like a water reducer because it doesn't
Okay.
really change the slump of the concrete. But what it does do is make the concrete more workable, and that
Okay.
can allow workers to place stiffer concrete, if you will, without having the problem. Here, an example is it typically will cut pump pressures. If you're running concrete through a pump truck, it'll cut pump pressures generally about half because of
Okay.
its ability to help the concrete move. So excellent
Yeah.
point. But if you were to ask me what we would do or what we would recommend for a watertight structure, it's going to be the spray applied, because
Okay.
the integral does reduce pore diameter, but it doesn't shut it off completely.
I guess it depends on the application. I mean, one needs to then
It
just
does.
consider the type of application. And
Yes.
at the end of the day, I guess comes down to scale of economies. You want to use the most
Mhm.
effective. And again, yeah, I guess is it more cost effective to mix it during or after? At the end of the day, money is money.
It
You
is.
don't have money to waste here.
Yeah, and it's going
Okay.
to depend on the thickness of the concrete comes into play in that point too, whether surface application or an integral use of the product is best for the project. It's a great point.
Okay. No, thanks. Okay, so then let me go to my panelists now, and then just to there have been a few questions that I had prepared. So I'll start, Lewis. I'll start with you. Looking at now, both the work that's been done by Brent, from spray oxide, and just looking at colloidal silica, and then obviously with your side, looking at alternative materials such as, like, your e-waste and plastics, and for its use as aggregates. And just to see how can we, combine the two? Because I do recall, I think in your uh, one was quite key and critical, especially when it came to that, producing that waste plastic aggregates. The binding was quite critical. I'm just wondering now, would colloidal silica, assist in that, or maybe you can just share your views around colloidal silica, Lewis.
All right, thank you, Takia, and thank you, Brent.
Thank you, Lewis.
All right, so indeed, I do have just a bit of a comment here and there, and just a little bit of clarification that I would like. I'm just looking down, I've written down just a few
Yep,
things here,
go for it.
as well.
Yeah.
So just to be, have some clarification, is that your colloidal silica is very much the same as silica fume, correct?
Correct, but
All right.
smaller.
It's smaller, okay. And we also find that this CNS, let's just call it CNS, all right?
Perfect. Yeah.
Sorry, there it goes down. Yeah, let's just call it CNS for ease sake. What we find is that this product is manufactured synthetically, correct? It's not like silicate fume, which is then also not really man-made. It's more of an industrial byproduct from the ferrosilicon industry. But yours is completely synthetic.
Yes. I will say the majority of colloidal silica processes are synthetic. There is at least one company that I'm aware of that harvests colloidal silica naturally from geothermal type wells. I think they're out of New Zealand. There's a few different ways to make colloidal silica, but most of them are synthetic, yes.
Okay. And because it is so small, it is able to, penetrate the concrete fairly easily. But you do this generally when the concrete has reached its initial set, correct?
Correct,
All right.
yes. Initial set, about the time you can walk on the concrete without leaving a boot impression, is the earliest we want to see it go on.
All right. And what happens is that you have some capillary suction that occurs, all right, that's sucking it in, because obviously you have your concrete that's still fresh in its way. And what I've also noticed is that the CNS also provides then some nucleation sites and seeding sites within your pores.
Yes.
And so when you do have this reaction, as you were stating previously, in which you have your calcium hydroxide reacting to produce these calcium silicate hydrates, these are generally more refined than that of general cement hydration, correct? More dense.
Yes, great point. And yeah, and that's something that I sometimes forget to mention. The reaction, the form of CSH that's produced is generally going to be more resilient than even the primary CSH, meaning it's longer chain, it's more intricate, finer refinement. So the academic literature has at least 5 or 6 papers that I've studied specifically that reaction product and its differences and similarities to the original CSH cement water hydration reaction.
All right, that's very good. I just want to share my screen here with you, so you can also just have a look at what I'm going to just try to explain to you. Right, so I assume you can see this screen.
Yes.
Now, as you know, one of the weak links within concrete is the interfacial transition zone. It's completely different to that of the bulk paste. And this is shown over here. Generally, we find that the interfacial zone is a zone going from more of a higher porous microstructure to that similar of the rest of the bulk paste. And that we generally find, range anywhere from, people have said 5 micrometers all the way to 30, 35. I generally say it's around 30, 35, even though some might even go to 100, which I do not necessarily agree with. So if this is true, and we have this colloidal silica that you're proposing, I think that since it is that small and it can create nucleation sites, and since we find that generally the interfacial zone is more porous than that of the rest of the bulk paste, you will most likely find that you will have additional, or let's call them secondary, calcium silicate hydrate gel that is formed between the bulk paste and then obviously refining the interfacial zone. So I would expect that indeed using this colloidal silica will result in perhaps a more refined ITZ. And obviously, if you have a refiner interfacial transition zone ITZ, you can expect that you will have improved durability and most likely strength. Okay?
Yes.
So I think, if we look at this, just to go with what Takir was saying, is at the bottom, we find that we have a BSE backscatter electron image. The brighter points that you see here are unreactive cements, while the darker points are pores. And if we had to then, segregate or just move the ITZ, segregate the pores, we can clearly see that utilizing these plastics does result in higher porosity or higher porosity at the interfacial zone compared to that of what we find with our pastes. Now, indeed, that could happen, and we can have some refinement. But I was just wondering what your view is, because you mentioned durability.
Yes.
And, what we find generally, more often than not in industrial areas is that our buildings are attacked by, sulfuric acid in the form of, for example, acid rain. All right. Now, your this CNS that we have over here, how does that compare to sulfuric acid attack when potentially, instead of utilizing CNS as a surface treatment, I suspect that it's a multifunctional system that you have. How does that compare then to perhaps rather utilizing a different surface treatment like nanoclay, which is a little bit more on the environmentally friendly side? But how would you then, compare the use of CNS with that of potentially alternative surface treatments when looking at sulfuric acid attack?
Yeah, what a great question. I know very little about nanoclays, but if the dispersion package and the way that those nanoparticles are kept from flocculating, because nanoparticles from van der Waals forces and other things, they like to clump, and so that's why we're producing the nanosilica in a colloidal form rather than as a bulk powder. So the key to performance, yes, the particles should be reactive, but we have to get those particles where they need to be effective, around to be able to penetrate into the concrete, to get to the ITZ, to refine that pore structure is going to require some chemistry on the dispersion package side that allows that product to penetrate. So yes, it is it is a capillary rise type of penetration, but it's more than that. So if you take the colloidal silica product that I work with, and you take deionized water and you put them both on concrete, the colloidal silica penetrates about 4 times deeper vertically, okay, upwards than the deionized water. So there's an attraction that I can only assume is an ionic attraction of some kind to be pulling that into the concrete. Now,
some form of electrostatic force.
Yeah, it's more than capillary rise, but I can't. Our product, or the product that I work with, is not. There still needs to be some more study done on some of those things. For instance, I would love to have visual evidence that our product does close the ITZ. I don't have visual scanning electron microscope evidence, for instance, that it would do that, but I do have the observational evidence that it's doing that on things like chloride diffusion. If you don't shut down the ITZ, your chloride diffusion is not going to change. So the chloride diffusion numbers indicate to me that we're getting tremendous pore refinement, but it's not a direct measurement. So I would, if you have the ability at your lab to do a direct measurements, then you and I should work together. Yeah. But I don't know about the nanoclays. I'm sorry about that. But the key, and that's a long answer, but the key is going to be the dispersion of those particles to allow them to be where they need to be, rather than clumping.
Or can one say that perhaps maybe why, coming from a layman's point of view, that why you're making synthetically is just so that you can try and control the rate of dispersion. With a natural product, it can be a bit uncertain. Might be maybe another way to look at it.
That is a good way to look at it. For us, the way that the product's made is something that is a synthetic process, but that synthetic process is key to controlling the particle sizes, the particle size distribution, all of those things, all of those QC items. We're an ISO 9001 manufacturing facility, so we have to make sure that we're spot on. And with a natural material, that'd be much more difficult.
Yeah, and maybe just to touch on that, sorry, Lewis, maybe if I can try and rephrase one of your questions that you had regarding the making use of natural materials, and I think it comes down to the question of sustainability. Would one say that perhaps maybe the angle, it would be that long term, that because you wouldn't have to replace concrete that often, then there's a benefit of the greenhouse gas emission reduction, in that you don't need as much concrete. Again, I'm just coming from a layman's point of view. Lewis, I don't know if that's what you're also looking to try and maybe get at.
No. The other point that I wanted to say was maybe just to mention this to Brent, is that we've saw the ITZ between the natural aggregate and the bulk paste, as well as that in plastic, and then again the bulk paste. But generally what we find with the use of demolition aggregates is that you have your natural aggregate. Generally, you will have a piece of mortar, or you will have some of the old mortar paste that is stuck to that aggregate. Generally, that is the case. And if you had to then use those very same aggregates, you will form a secondary ITZ, because you'll have the original aggregate, the ITZ, the old paste, then you'll have the new paste, and between those two, you'll have another ITZ. And I think maybe one route in which this CNS could significantly help is by improving the durability, potentially the strength, is by then refining all of those interfacial transition zones, and I think there's some future research for that.
Yeah, and reducing absorption of the recycled aggregate as well. The recycled aggregate, at least here in the States, 3 to 6 times the absorption rate of a natural an aggregate that's mined or naturally occurring. So that makes it very difficult from the practical standpoint of using those recycled aggregates in actual real world concrete, because the concrete producer is chasing a water demand that's doing this. So if colloidal silica could be used to reduce that absorption rate and stabilize that absorption rate, even if it's still a bit higher than a natural or mined aggregate, if it was stabilized, then it could lead to more use of the recycled concrete aggregates, which would then be more environmentally friendly.
I see a potential collaboration of you and maybe future experiments. Lewis, between yourself and Brent, colloidal silica versus the e-plastics. Just mash the two together, and then an interesting paper.
Well, even the e-plastics, if we can shore up that ITZ a bit in the plastic aggregate, even it could be potentially helpful. And that's something that if I'm sure we could get you some product to play with if you'd like.
Thank you, Brent.
No, thanks. Okay, colleagues, I think then let me move on to some hands. I want to make this an interactive discussion with you as the audience. So I'll take at most 2 hands, and I'll just continue with my questions on the side. I see we've got the Gideon. Gideon, let me take your hand, and if you will take a second hand, if anyone has put up their hand. I'll maybe just check the third one. I'll do a comment from the chat box. So Gideon, if you can come through. Thanks.
Thanks, and thanks for the very interesting presentation. Just for reference, talk about layman. I'm an electrical engineer, so be gentle. But I look after infrastructure in the rail environment. 2 questions. One is for mast foundations that you dig into the ground a whole 2 meters deep to keep your, from overturning. Obviously, you can't spray it afterwards. So in that case, I'm assuming you will just go the whole hog and mix it in.
Yes,
that's my first.
That would be my recommendation. Yes,
and
and that goes for any foundation you can't reach by spraying.
And then a second one, we've got bridges in the coastal areas that are extremely exposed to salt spray, and we've got a lot of spalling with rebar expansion, like you mentioned. When you repair that, would you, once you've chopped everything away and and cleaned it up a bit before you do the next phase and put the rebar back and cover this with cement again or concrete again, would you suggest that you apply this particles before you put the layer back, so you can sort of increase the strength of the existing bridge, whatever is left of it, before you put the rebar on? Or would it be okay to just do it after you've put the new concrete on?
So we do have a reinforced concrete repair guide that I'd like to share with you, and it does detail if I don't remember if or I don't know if you took down my contact information, but Takir has it. So I would need a way to get in touch with you. But so the idea would be our recommendation generally is do the repair, remove the unsound concrete, get back to the finger width or however deep you want to be behind the rebar. Go ahead and treat the concrete with the colloidal silica, spray applied colloidal silica. And then if you use a cementitious patch or something that will accept the colloidal silica, then you can retreat that patch, but you're also going to want to treat the surrounding area. And the reason is that you're going to want to avoid the what's known as the halo effect, the anodic ring phenomenon that happens when you do a repair, where you have areas of high pH to low pH. That repair can make a battery that can accelerate additional reinforcing steel corrosion. So you're going to want to stabilize that concrete and make it the permeabilities as similar as possible from the surrounding concrete to the patch material to the substrate concrete. So that was a great question, but we do have a generalized repair guide that could provide some more guidance on that.
I just want to check then, Brent, including this presentation, is that something that you can share with the audience?
Oh, yeah, that's fine. Yeah.
Because what we can do is that post this discussion, I can always just email it to everyone that is online. So we do have your email addresses from the registration. So we can just email it to everyone. And then also your contact details, we can also email it to everyone. But if you have the time, yourself and Prof. Or Dr. Lewis, just to drop it in the chat box as well. Yeah, I remember I once called Lewis Prof and said, no, not Prof, Doctor. Yeah. Okay. If there's one other hand, do put up your hand, colleagues. I'll then just go on to the chat to see if there's anything at the chat. Let me just go here. We'll take one from the chat and I'll continue with my questions. Okay, let me just see. Yes, okay, so there's something about CPD. We can then discuss that offline. Can colloidal silica be... Okay, so this is a question from Levi Kamanga. Can colloidal silica be effectively combined with other supplementary cementation material to reduce total cement content?
Yes. And what I mean by that is your everyday concrete, your 20 to 40 MPa type concrete, generally doesn't have enough powder content to be removed or reduced. But if you have, let's say you have a durability requirement on a bridge, for instance, but the strength requirement's only, let's say the strength requirement's 50 MPa, but the durability requirement causes you, whether it's the oxygen permeability test or whichever test it is that you're beholden to, where you have to have more cement and a lower water cement ratio than is needed for strength to hit those OPI numbers. That's where colloidal silica really shines, because you can take a normal cement mix, a regular, like a 40 MPa type cement mix, treat it and get the durability of an 80 or 100 MPa mix. Even so you're economizing your cement use by using the colloidal silica for the durability properties. So that's the big strength of colloidal silica when it comes to that, is saving that extra cement.
Yeah, and I guess it comes back to just a comment earlier on, is that depending on the application, one needs to weigh out the different factors and see what's the most cost effective and most effective solution. But yeah, I think also, colleagues, I think one of the key things that we're trying to drive today is that there is innovation happening within the industry, and lots of different options available, and we won't know until we test them out. And typically, that's where now universities come in, research institutions come in, some companies have their own research, and you need to do the research, test the different things. Like chemistry. If you think about the alchemists of the past, just throw everything together and just see what happens. I mean, that's basically what you're gonna have to do. And then you've got a hypothesis, you test it, it works, it doesn't work. and then you carry on. So yeah, it's we are in exciting times with all these new materials, but we need to test them out in a controlled fashion. I'll take one more hand from the audience, and I'll just got a few more questions from my side. Jadidi, if you want to come through and just ask a question, thanks. Jadidia, apologies.
Okay, thank you, sir. Maybe I'll just start by commending, is it Dr. Rollins or Mr. Rollins? I'll
It's
start by
Mr.
commending your discussion. I think your presentation was actually very insightful,
Oh, thank you
and
very much.
I can concur with Mr. Ahmed that yeah, we're really faced with exciting times as far as such materials are concerned. If we're talking about something that really outperforms things we are used to, like your fly ashes and so forth, I think we are really into something. However, I do have a question. My question, I think, is based on something you touched on earlier, which is a concern with something like your fly ash as well. Availability and cost. Is this material prevalent? Are there projections on when it might be so prevalent to a point where it can be easily accessible? Because like one gets to see a lot of opportunities as far as its applications are concerned. However, judging from history, I remember I was also once involved in the ready mix industry, and it used to always be said that, in fact, I think I only encountered fly ash in the ready mix industry. As far as the other industries were concerned, fly ash was really non-existent. You go on sites, you find that people are really not willing to adopt that technology at all. So the adoption rate was something else as compared to what the product will offer. So in this case, we can see that we do have a material which can give us a lot of opportunities as far as maintenance, as far as the life cycles of our infrastructure is concerned. However, is it going to be easily accessible and cheap enough for people to adopt it at a much faster rate in the near future?
No,
Sure.
thanks,
Thank you.
Jadidia. And if before we come in, Brent, it's leading on to a question that I also had. I was going to ask that, when it comes to these innovative products, and especially convincing the market to buy in. What's the your biggest non-technical barriers that you've encountered, and how do you overcome that? And then I'm going to come through back to Lewis with a similar question. So yeah, if you can just maybe give feedback on the few questions, Brent. Thanks.
Sure. Thank you for the question. Thank you for both questions. First, let me say that I have to speak from my experience, which is the company that I work for. I don't know a lot about the other producers of colloidal silica, but I will tell you that South Africa is our biggest international market by far already. So we do already do quite a bit of work in South Africa, and Spraylock Africa is based out of Joburg, and we've done projects across the country over the last, since about 2012, I think is when we were first starting in South Africa. So there's a history there. As far as cost goes, it's not a cheap product for sure. But I mean, I have to do. Spraylock Africa is who we rely on for pricing, but I'll try to give you a ballpark, if I may. Let's see. I'm doing a quick calculation to make sure where we are. Yeah, you're going to be somewhere in the neighborhood of probably, for the spray, somewhere in the neighborhood of maybe 200 rand per square meter. something like that.
Mhm.
So
Yep.
let me just I think but that's something that if you were more interested in nailing that down, and I went high on purpose because I don't know what my distributor charges the market. That's something that we supply him and he supplies the market.
Yeah.
So I went high, but I can put you in touch with the Spraylock Africa representatives there.
Yeah.
But as far as the other question, Takir, if you don't mind, if you can remind me, what was the second
just,
part?
when it comes to innovations like this, and I think it leads back to maybe also, I guess, can we just maybe answer the question that Jadidia had, is that can one expect this to become more cost effective over time as technology improves?
Yes,
Naturally,
yeah,
it would.
and as suppliers and as additional suppliers began selling the product, more people began manufacturing the product specifically for concrete. Yeah, the price will come down. It is cost effective if you look at it from all of the things that colloidal silica can assist with. So we can work through that with you and show you how to save some money in some other ways. But as far as
minus the
what you
escalation
get from it, it's a value. Sorry, go ahead.
Yeah. No, I think obviously minus escalation there, because that also needs to be taken into account. But naturally, well, it would naturally become cost effective. But again, I don't want to delve into a market that's your market. Again, I'm just a layman. So the question that I was asking is, just a follow on to Jadidia's comment as well, is that when it comes to this newer type product, it's new innovation, it's new to the market, and obviously, as Jadida also mentioned, that even when it came to still the case with fly ash, there is still that uncertainty in making use of these materials. So for you now, from a technical point of view, being a technical expert, and I think let's just look at from just pure, being the specialist in it. You see the product work, you've got the science that backs you up, but then how do you convince the industry in taking up this product? And again, to try and break those barriers of uncertainty and the like. Yes. So, what have you seen as biggest technical, non-technical barriers from your side?
Great point. Technical barriers is I'll start with that. And the technical barriers are you have to find a place in the standards for the material. And right now, there are very few specific colloidal silica standards. We're working hard to make that happen from on the American side. ASTM has 2 specifications we're working on for colloidal silica at the moment and have been for 7 or 8 years. It's a slow process. SANS there has also been working with to try to get some colloidal silica recognition in some of those documents as well. So technically, it's getting into the documents. The science is there, but when you have a consensus organization, especially, producing a document that is acceptable to everyone with a new technology that is potentially game-changing, steps on a lot of toes, and people become worried that you're going to replace this item or that item. So building that consensus, having an overwhelming number of academic papers regarding the technology, and there's over 100 that I'm aware of, those are big points on the technical side. And I know we're limited, and I'll try to speed this up. On the non-technical side, people don't like change. What we do, the way we approach that, and especially engineers, you guys have a really important job considering life safety. And so the approach that I'm taking with the company I work for is to provide products for testing, provide products for demos, to try to overcome some of that hesitancy.
Yeah. No. Again, that's a very great approach. What they call it, the proof in the pudding is actually eating the pudding. Sorry, let me just mute the colleagues online here. But definitely, I mean, there's one approach to look at it. And colleagues, I know we've got about 4 minutes left, but if you don't mind, just a few minutes over 6, so we'll just to fit in just 1 or 2 more questions. Lewis, just coming back to you on a similar question, and I think from your side as an academic, and not specifically on Colloidal Silica, but just from an innovative point of view. Obviously, from your side, similar to your e-waste, you'd look at this innovation, you come up with the research, but now it's a matter of convincing industry to then uptake this, because also at the end of the day, one would think now, and then it was a question that I was going to ask, but I'll just summarize the question that as an engineer, if you look at now, we are governed by EXA, and we need to also at the same time make sure that we stay up to date with the latest technology and make use of that. And if we know that there is technology available that can greatly, improve the life of infrastructure, and not only that, secure the economy and secure safety. I mean, it's almost like a no-brainer and almost unethical to not adopt that. So with that in mind, and from your side as an academic, and from doing the research, how do we try and convince industry, when it comes to new innovation? Just your comments and views around that.
All right, thank you for that. It's a good question. And you have to remember that, the structures that we build are being used by humans. And the last thing that we want to do is to use a type of technology which isn't necessarily tried and tested. So indeed, we might have something that is some magical formula that can maybe produce concrete that has 200-300 megapascal in strength. All right. But maybe we find in 5 or 10 years, we have some problems that have developed. And now all of this infrastructure could either have seriously injured or perhaps killed somebody. And therefore, you need to be very cautious when implementing and adopting these products and standards. So unfortunately it takes time, but if we look at the waste products such as fly ash, such as condensed silica fume, such as GGBS, which is now very much considered a standard, and actually it is almost required because of the increase in durability, especially in the coastal regions with GGBS. It is almost required that it is used within your concrete product. And so unfortunately it does take some time. There's good reason for that. And the best way is to start with smaller scale projects and then monitor that as time progresses.
And then obviously Lewis, look, we've got now in South Africa, you've got now your SABS. You've also got agreement that normally does these material testing. So I take it with yourself as an academic, do you normally get involved with SABS through working committees? Just to maybe give insight into how some of these products normally would get adopted as standards.
So at this stage, I'm not working at that at all with SABS at the stage. My studies, my work on plastics within concrete, are just in small scale, trying to see how can we improve it before bringing it trying to bring it into practice. So no, the whole idea of this utilizing of alternative materials is a bit in the development side.
Still quite new.
Yes.
So still a bit of research that needs to be done, and I guess with the likes of SABS and agreement, because I understand from their side, and they would also do quite rigorous testing and research themselves before they actually put their mark on it. Because I know, especially in South Africa, if something's got the SABS mark, it's then deemed as 100% good to use. Okay. Colleagues, we've pretty much come to the end. What I'll then ask, just for let me get to my final question here. Okay, so whatever questions I didn't cover today, I'll try and get the presenters just to answer it, and we'll do some sort of maybe article out of it. But I'll engage with yourself, Lewis and Brent on the side. So just in parting, I'll start with Lewis, and then we'll go to Brent. So just your final thought, and again, what's the single most important message or call to action you would like the audience of engineers and other professionals online to take away from today's discussion?
All right. Yeah. Again, very good question. And I think when we look at, the properties of concrete, we're very much accustomed to, if you have a strong concrete, then your concrete will be durable, which isn't the case at all, right? Strength and durability are not very good correlated. You can have a strong concrete, but very poor durability, which is something that we're finding these days. And especially, I think there were a few, classrooms that have that I think collapsed in the UK because of this whole idea. So the concrete was strong enough, but durability was a problem. So just always keep that in mind, and we should start to look at utilizing smarter materials and methods in order to improve the resilience of our infrastructure, our future infrastructure. Yeah.
No, definitely. Testing research, very important. Brent, your closing thought?
Yeah, excellent, Dr. Parsons. I wholeheartedly agree. My main statement regarding today's talk is that while recycled content is important, I think we need to do a better job of looking at the predicted service life of structures, and using not just our embodied carbon for making a material, making a cubic meter of concrete, but also look at the total greenhouse gas load from a cradle to grave approach, so that we get some information from that extended life time, and we look at it from both angles. I'm not saying we should abandon cradle to gate. No, we certainly should use recycled materials. However, let's also make our concrete last much longer.
Yeah. It's a balanced approach. As it goes, what's the most cost effective, and also from an environmental point of view. So thanks for that, Brent and Lewis. And so collect just from us just a few closing notes. And again, questions I didn't answer, do drop it in the chat. We'll make a plan to try and get it to both Brent and Lewis, for them to then give us feedback on. So we do have now, you would have seen now for this month, we've set up the email account for SAICE, Knowledge Trailblazer. So you would have received your invite from there, and we'll try and make use of the same platform for any further comments and questions. And again, if you do want to post today's discussion, want to reach out to both Brent and Lewis. So if we haven't given you their direct contacts yet, you can make use of the same SAICE Knowledge Trailblazer email address, just to give us that feedback and response. Because typically once this session is ended, I know normally getting access back to the chat is a bit limited. So just a few notes from as I was jotting down some notes. So when it comes to concrete industry and greenhouse gas. So again, concrete industry is quite significant, in terms of greenhouse gas. And I just did a quick check online. 8% of greenhouse gas comes from the concrete industry, so it's quite significant. And again, as Brent also then highlighted early on, I think you quoted, 60 or 40%, recycled, or we just replacing existing concrete. So again, you want to make sure that your concrete lasts longer. And as you pointed out, that some of it being from the porous nature of concrete, it does impact the durability and longevity of it. So again, concrete is meant to last. And again, I want to come back to the Roman concrete. It's been around for almost 2,000 years. So if they can make something last for 2,000 years, I'm sure we can do something similar. Again, it could be something to do with that, the volcanic ash. They did cook it. I know the one difference is that they cooked and they boiled the concrete before they poured it. Something there we need to look at. But yeah, again, we want to make sure these things last longer, so that we try and reduce the amount and volume of concrete that we use, and then that naturally should then come back to reduction in greenhouse gas. So yeah, and again, thank you both, Brent and Lewis, for your insights. And so we explored, the vital importance of continuous innovation, rigorous research, and responsible implementation in civil engineering. Again, so materials like colloidal silica can offer pathways. So it's just one of many types of materials that you can get. And so we also then discussed and highlighted, the other careful consideration when it comes to new technologies. the long-term value that they do bring. Again, there needs to be standardization. We do have our standardization bodies that need to then also put their stamp on it and adopt these new innovations. So there's a specific obviously pathway to that we need to then follow. Again, understanding the underlying science is quite critical. Evaluate the long-term benefits, stay informed about evolving standards, and actively participate in dialogue. So yeah, again, when it comes to these things, so we've got academia here, we've got industry, and that's where the magic happens when we come together as different parties of the industry. We've got various aspects, as I highlighted earlier on, is that you've also got your professional bodies, you've got your stand bodies. We all need to come together to make these things work, and in a very effective way going forward. So just to give you an insight, next month's SAICE Fireside Chat, we'll be looking, we're going towards the IT side and the AI side. So we've got a company called Sub8 who's going to come and give us a presentation on structural and geotechnical wireless condition monitoring. So something quite interesting there, with AI and technology. So keep an eye out for that. And then, yeah, again, just to reach out to those who are not members of SAICE and who are perhaps maybe not within South Africa, but are interested, we also welcome you to join. So I did drop the link in the chat for the membership. So we strongly encourage you to join us, and especially the civil engineers within the country, do join us and then become a member of SAICE. Brent, you're more than welcome to become a member of SAICE as well. We'll
Thank
reach
you
out
so
to you
much.
for that. Those things.
Yes, please.
And yeah, and then for those who are interested in giving a presentation in the future, again, we are open to that. If you want to give us a presentation, then drop me an email, or when I do send out the email from the SAICE Knowledge Trailblazer chat. And yeah, I think before I close off, I see we've got Uncle Tom. Uncle Tom, do you want to come through before I just say my final parting shot?
Yeah, Takia, just in case they're unaware of it, we are launching probably early next week webinars on demand. And we're starting off with the fireside chats, given the success of them. So you will be able to go into SAICE's online on-demand portal, and for a very nominal fee, you'll be able to go and review any of the webinars and earn CPD points. A little bit more difficult than attending live, because there will be an assessment on the content. So I will take Brent's presentation today and get AI to help me generate some questions with the right answer, because I wouldn't be able to answer the questions or similar. But it also allows those that miss out on the time cutoff to go at least and still get the points, and or for those that miss the session to get the points. So just watch the space. We will notify you via the Knowledge Trailblazer email in due course once those are up and running. But thanks, Takia.
No, thanks, Uncle Tom. And Brent and Lewis, if you guys don't mind, maybe Uncle Tom, if you want them just to maybe answer some of the questions, so that when you do have that assessment, that they can also then assist with giving you some input, if that's okay, Brent and Lewis.
Yes, of course.
Okay.
Perfect.
No,